Welcome to the deep dive. Today, we're diving into a really big challenge in the world of large language models. How do you make them faster, especially, when they're processing these super long texts or conversations? And crucially, how do you do that without losing any of the quality? Turns out a key technique here is something called speculative decoding.
That's right. And today we're really focusing on one specific paper. It's called LongSpec. Long context, lossless speculative decoding with efficient drafting and verification.
Oh.
So our mission really is to unpack why the current best methods for speculative decoding, the ones that work great for short texts, kind of fall apart when you try to use them for really long sequences. And then we'll get into how LongSpec uses some, frankly, very clever new ideas in its architecture and algorithms to get around those problems.
Okay, so the big question, and this is where I think it gets super interesting, is the one the paper poses right at the start. Why cannot SOTA SD methods for short contexts be directly applied to long sequences?
Mhm.
It sounds straightforward, but yeah, the implications are pretty huge. Let's start by unpacking that core problem.
Yeah, it's fundamental if you care about long context LLMs. The main issue, and the paper lays this out really clearly, is that these state-of-the-art methods, the SOTA ones, they often rely on the entire target language model, the big, powerful one, just to generate the first guess, the draft sequence. Think about it like asking a master painter, super careful, to just quickly sketch something out. It's not the best use of their time, right? These full models are just too heavy, too slow to generate those drafts quickly enough for speculative decoding to really work well, especially as the text gets longer and longer.
Right, that makes a lot of sense. So the paper flags three specific challenges that pop up when you try to scale these short context methods. First is the need for a memory-efficient architecture. You mentioned the draft model needs to align with the target model, and apparently existing SD methods often need the draft model to look at the target model's internal workings, like hidden states or this thing called the KV cache.
Exactly. The KV cache, you can think of it as the LLM's short-term memory, its working space. Every time the model looks at a new word or token, it stores a little summary, the key and value for that token. This is how it remembers what's already been said or written without rereading everything constantly. Super important. Now, for the draft model to make good guesses about what the big model will say next, seeing this KV cache is really helpful. It aligns them. And here's the catch. As the text gets longer, that KV cache gets enormous. If your smaller draft model needs to copy all that or even just access it heavily, boom, you've got a massive memory problem.
Okay, yeah, I see. And that ties right into the second challenge they mention, scalability. Most draft models are apparently autoregressive, meaning they build the text word by word, looking back at what they just wrote. And each step needs that KV cache we just talked about.
Precisely. So you've got your main target model holding this huge KV cache. Fine. But now your supposedly lightweight draft model also needs to maintain its own big KV cache. Suddenly, you're using up way more GPU memory than you'd like. Think about tasks like LLM agents planning complex steps or really long reasoning chains. The output can be massive. You can just run out of memory, even on really good hardware. It becomes a bottleneck. Right. And then the third challenge is simply speed limitations. If the draft models themselves are built using parts of or rely heavily on these heavyweight target models, they just can't generate drafts fast enough. Exactly. The whole point of speculative decoding is speed. If your draft generation is slow, the benefit starts to disappear. So putting it all together, what this means for you, the user, is if you're trying to use LLMs for long chats, analyzing huge documents, or doing complex reasoning, you hit these limits. Things run slower, and it costs more in terms of computing resources. It kind of defeats the purpose of using an acceleration technique in the first place.
Okay, so given those hurdles, it's really helpful to look at how speculative decoding evolved to get us here to LongSpec. The basic idea of SD, just to recap, is speed up generation without changing the final output quality. Same result, just faster.
Spot on. And the journey is quite interesting. You had early attempts around 2023 from folks like Zhi et al., Leviathan et al. They basically tried using existing smaller LLMs as the draft model, like, junior assistant sketching for the senior expert. Then others, like Sun et al., worked on making those junior assistants a bit smarter, more efficient. We also saw some neat tricks, like Liu et al. In 2024, where they repurposed parts of the big target model itself to act as the draft. Clever. And then there was a totally different angle, retrieval-based SD from Fu et al. This used n-gram matching, finding common word sequences to build drafts. The cool part, no extra model training needed at all. But more recently, things got really exciting with models like Medusa, EGLE, and Glide. These really moved the needle. They didn't just grab an existing small model, they designed specialized draft models, and they introduced these more complex tree speculation techniques, where the draft model proposes multiple possible futures like branches on a tree. This gave much better performance and efficiency.
Right, and that brings us right back to LongSpec. Because even a really successful model like EGLE, which was a big step forward, it still depended heavily on getting those hidden states from the target model, and it used that autoregressive structure. And that autoregressive part meant it still needed its own KV cache, leading right back to that memory overhead problem for long context we talked about.
Exactly. So even with those advances, the long context bottleneck was still there. And this is where LongSpec really shines with its specific innovations. Let's break down their memory-efficient draft model architecture. To get that constant memory usage, no matter how long the context, their draft model has two main parts. Think of it like two specialized processing units. One is a self-attention module. It focuses just on the local context, the words immediately nearby. The other is a cross-attention module, and its job is to grab the important information from the entire long sequence, the long-range stuff.
Okay, local and long range,
Yeah.
but how do they stop the memory growing?
The key trick is in the self-attention part. They use a sliding window attention mechanism. They cap the window size at 512 tokens. So it's like reading a super long scroll, but you only really focus hard on the last page or so. This physically limits how much memory that part can use, directly tackling the scalability issue. And they actually prove mathematically in the paper that doing this, approximating the attention, doesn't really hurt performance much.
Clever.
Okay.
What's next?
Next up is the anchor offset indices strategy. This is super cool. It's how they handle position information in these massive sequences. You know how normally words are numbered 0, 1, 2, 3? Well, that gets tricky with tens of thousands of tokens. So what they do is reserve the first four positions, 0, 1, 2, 3, as special attention sync tokens. This taps into something called the attention sync phenomenon, where LLMs naturally pay a lot of attention to the very first tokens. It kind of anchors the model's understanding. Then, for all the other tokens, they assign these big consecutive numbers, but, and this is key, they start at a random offset. So instead of 4, 5, 6, it might be 0, 1, 2, 3. There may be 8, 192, 8, 193, 8, 194, and so on.
Random offset. Why random?
Good question. It's to make sure the model gets trained on seeing all sorts of position numbers, not just the small ones here at the beginning. It makes the positional understanding more robust. And they found this weird indexing only increased the target model's error by a tiny, tiny amount, like a 0.0001. So it works really well without messing things up.
Wow, okay. That is clever. And the third innovation?
The third one is the hybrid tree attention mechanism. This tackles speed bottlenecks in the verification step, especially when using tree speculation. It's based on two main insights. First, when the target model is checking the draft, the calculations involving the existing KV cache from already processed tokens don't need complex attention masks. They call this K-cache, V-cache. Second, only the calculations involving the newly proposed speculative tokens, the draft, actually need careful masking. They call this K-specs, V-specs. And usually there aren't that many of these speculative tokens at once.
Okay, so they treat the old context and the new draft differently.
Exactly. They use a divide and aggregate strategy. For the big chunk of existing context, K-cache, V-cache, they use a super fast, optimized calculation method called flash attention, or flash decoding, made for speed on long sequences. For the small set of new speculative tokens, K-specs, V-specs, they use a custom-built kernel using Triton, a language for GPU programming, that handles the necessary masking efficiently. Then they combine the results from these two parts. The paper goes into the math in the appendix to show this combination is mathematically sound. It gives the correct attention output. Okay, that is some serious engineering. Designing the architecture is one thing, but how do you actually train something like this? It feels like juggling a lot of moving parts. It definitely is a process, but they laid out a pretty clear multi-stage approach. First, they worked with several well-known target models, Vicuna, LongChat, Llama 2, Llama 3.1, even QWQ32B. And they made sure the draft model's configuration, like the number of KV heads, matched the target model it was paired with. Consistency is key. Then the training itself happened in 3 stages. Stage 1. Pre-train the draft model using those anchor offset indices. They used a big dataset, Slim Pajama 6B, and varied that random offset they used for positions. This teaches the draft model the basics of handling those weird position numbers. Stage 2. Train it specifically on long text data using a subset of something called Prolong 64K to really build its long context ability. Stage 3. Fine-tune it. They created their own dataset for long context supervised fine-tuning, SFT. This is where it learns to generate really good draft predictions for the kinds of tasks they care about.
Right, so pre-training for the basics, specialized training for long text, then fine-tuning for specific tasks. Makes sense. So after all that work, the billion-dollar question, does it actually work? What do the results look like in terms of real-world performance?
Oh yeah, the results are pretty compelling. LongSpec consistently beats other methods, often by a significant margin. They measure not just the raw speedup, but also the average acceptance length. That's basically how many tokens, on average, the target model accepts from the draft model's suggestion in one go. Longer is better means fewer steps. So, for example, in summarization tasks, with low randomness, they were getting an average acceptance length of about 3.5 tokens. That translated to speedups of up to 2.67 times compared to just one of the base model.
2.67 times faster. That's substantial.
It really is. And for code completion, it was even better. Average acceptance length around 4 tokens and speedups hitting up to 3.26 times. It really shows the approach is robust and works well across different types of long text generation. Even when you increase the randomness, which usually makes speculative decoding harder, LongSpec still maintained a solid lead, giving around a 2.5x speedup compared to another method called MagicDec.
That's impressive, especially the code completion numbers. What about those really long reasoning tasks you mentioned? Things like LLM agents planning or complex problem solving. Is it good for that too?
Yes, the paper specifically highlights that LongSpec is particularly well suited for those scenarios. These are cases where the input might be short, like a question, but the LLM needs to generate a very long step-by-step answer or plan. LongSpec's efficiency and high acceptance rate really help here, tackling both the speed and the memory challenges inherent in generating such long outputs. They also looked at throughput, how many tokens per second the whole system can handle. Across different batch sizes, LongSpec consistently processed more tokens per second than both the standard baseline model and MagicDec. For instance, with a batch size of 8, LongSpec hit over 560 tokens per second, while MagicDec was around 310, and the baseline was under 290. So nearly double the throughput of the baseline.
Okay, wow, so it's faster per generation and can handle more requests concurrently.
Exactly. They mentioned running this on 8 A100 GPUs using specific memory optimization techniques like zero. And they had another clever optimization related to that tree speculation stuff we mentioned. Normally in bean search, which tree speculation uses, if a path looks unpromising, you discard it. But in speculative decoding, discarding nodes can mess up the KV cache and slow things down. So LongSpec does something smarter. Instead of fully discarding a bad branch, they just stop computing anything further down that branch. They prune it without the costly cleanup. Very neat trick.
That is clever. It preserves the efficiency. And, it makes me think back to the KV cache itself. It seems so central. Why exactly does having the draft model align with the target model's KV cache help so much?
Yeah, it's a fundamental point they touch on in the appendix. Basically, the KV cache represents the model's understanding of the context so far. If both the draft and target models are looking at effectively the same KV cache, or a draft cache derived directly from it, then the main reason their predictions might differ comes down to their internal parameters, their knowledge, rather than having different interpretations of the preceding text. It removes a major source of potential disagreement, making the draft model's predictions much more likely to be accepted by the target model. They're starting from the same page, contextually speaking.
I see. So it ensures they're working off the same memory of the conversation.
Precisely. And this isn't just theoretical. We're seeing companies like DeepSeek and Google starting to offer context caching services. The idea is to pre-compute and store these KV caches for common prefixes or contexts, which would potentially speed up things like training or fine-tuning even further. It validates this core idea about the importance of the cache.
Interesting. And you mentioned the paper also has theoretical backing.
It does. They include a formal analysis, like Theorem D.4, which mathematically bounds the potential error introduced by their approximations, like the sliding window attention. It essentially provides rigorous proof that the method is not just fast in practice, but also theoretically sound and unlikely to significantly degrade the quality of the output. It adds that layer of academic confidence.
Okay, so let's try to wrap this all up. We've covered a lot of ground with LongSpec. We've got this memory-efficient draft model using sliding window and cross-attention, avoiding that KV cache explosion. We've got the very clever anchor offset indices for handling huge positional information. And we've got the super fast hybrid tree attention for verifying the drafts quickly.
That's a great summary.
Right.
And the payoff is clear. Significant speedups, higher throughput, and strong performance on those really demanding long context generation and reasoning tasks.
It really feels like a major step forward.
I think so too. If we think about the so what here, this kind of work is crucial for making these incredibly powerful LLMs truly practical for more complex real-world applications. It's pushing us towards AI that can handle genuinely long conversations, deeply analyze extensive documents, and perform intricate reasoning tasks much more efficiently. It makes these advanced capabilities less resource-intensive and more accessible.
Absolutely. Which leaves us with a fascinating thought to consider. As these context windows keep getting bigger, we're already seeing models handle hundreds of thousands, even millions of tokens. What does this kind of speed up mean for the future? How might it change how we interact with AI? Imagine AI that can genuinely read and reason over entire books or massive code bases almost instantly. Think about fields like law, medicine, research, or even just having truly seamless, long-running conversations with an AI assistant. Making these models both incredibly capable and efficient really could reshape a lot of things. It's definitely something to keep an eye on.